So our mixing problem, we had a 150-liter tank, and we had flow out was 10 liters per minute. And then our flow in the second problem was 10 liters per minute with a 2 grams per liter solution. And we should say that our initial concentration, we're originally starting off with a 5 grams per liter solution. Let's see, do we need anything else? I think that's all of it. So that's all of our initial data. And what do we want to do? So we want to model this. I think in part A, it asks us to find the initial value. So of course our C0 we have. And our S, we are using to measure the total salt. And we want to come up with a differential equation that measures the total salt in the mixture. So our initial total salt is going to be the concentration times the volume. And so we had 750 grams of salt initially. Same thing as what we saw in the first part of the problem. And just like in the first problem, the total amount of salt at any given point in time is going to be whatever the concentration is at that point in time times the total volume. In other words, I think we actually had it solved for our concentration in general. How do I find the concentration of a mixture? It is the total amount of the substance divided by the total volume. So now what we want to do is we want to come up with a differential equation of what's going on with this guy, of modeling the total salt. So the difference is, so we have some tank. Let's say the tank is some big cylinder or something. And there's water coming out, and there's brine coming in. Let's assume this thing is rotating as well. It's mixing everything as it's coming in. But the concentration coming in is 2 grams per liter. The concentration coming out, well, what's going to happen? If I originally start with a 5 gram per liter solution, as that goes out, I'm losing more salt than I'm gaining in because the concentration is weaker. And so we should expect the concentration to be decreasing. One thing you can do to kind of check yourself is just do mental checks of what are limiting values. What should happen as time goes off to infinity? If I just let this thing run for an infinite period of time or for a very, very long time, what's the end concentration going to be? Our end concentration should be stable at 2 grams per liter because that's what's constantly being pumped in. In the first example, I think we saw that, well, since we were pumping just water in, well, if I'm pumping just water in, eventually we should expect that all of the salt will flow out and we'll just be left with a tank full of water. So one way we can model this, or at least break this problem down, is let's talk about the grams of salt incoming versus the grams of salt outgoing. So let's do incoming first. We want a differential equation, so let's just model it with our ds dt, the rate of salt, but let's add a subscript. This is the salt in. So this isn't the net change of salt, it's just the salt coming in. And how much salt should I have coming in? What should the rate be? Well, we're flowing in at a rate of 10 liters per minute. So every minute, I got 10 liters coming in. And of those 10 liters flowing in, how many grams of salt should I have? Well, the concentration flowing in is 2 grams per liter. And if we see our units cancel, the liters cancel, and we are left with 20 grams per minute. So there's 20 grams of salt coming in every minute. This is the same as saying, like, I could literally have two spouts. I could have one pumping pure water in and one pumping, just dumping salt in it. And if I had pure water coming in at 10 liters per minute and another sort of opening and I was just dumping in 20 grams of salt continuously streaming in, exact same situation. Okay, so let's try to take a look at our amount of salt coming out. So we got to do something similar. And well, I still have 10 liters per minute flowing out. And every minute, 10 liters. What is the total amount of salt that's going to be contained in those 10 liters? It's essentially the same process of how we found this one, right? I have 10 liters per minute coming in. The difference was that coming in, I have a fixed concentration. But the idea is, of course, that the total amount of salt is just the concentration times the volume. In this case, our volume, or at least our change in volume going out is 10 liters now per rate of time per minute. So of that 10 liter volume every minute, how much is salt? We would just multiply by the concentration. And it would be that many grams of salt. Of course, we want a nice differential equation with our variables of S and T. So we can make our substitution out for our C of T. And so we should get 10 liters per minute times the concentration at any given point in time is the total amount of salt at any given point in time divided by 150 liters. So of course the units here are grams. And so we see that the liters units are going to cancel and we should be left with a grams per minute as we expected in the previous case. And so now we just got to put those two together. Remember that ds coming out, it might be better to put a negative sign here. So let's go ahead and simplify that. Since we are losing 10 liters per minute, let's go ahead and make that negative. And when we simplify, we get S over 15. And of course, you can drop the the independent variable subscript or the sort of bracket notation there if you want and just have it as S over 15 negative. So the net change in salt is going to be the amount of salt coming in, 20 grams per minute, minus the total amount of salt we're losing, which should be S over 50. So this is our differential equation. Any questions on that? So this will be on the quiz tomorrow. Make sure you guys understand this example. Let's do one check and solve this differential equation to see what is the limiting value. So how do we solve something like this? It is a separable equation. Since I have only s's, how many t's do I have over here on the right? None, right? If there's no t's, what we want to do is take this entire thing, divide it over to the left to get all my s's together. So we have ds over, now 20 minus s over 15. And when I divide, I will get a 1 here, and I will multiply the dt over, and we will get 1 dt over on the right. Now the integral, we can just integrate both sides. Right side's pretty easy. Left side, you might want to do a u sub, if you're still want to write out all your steps. We have something like 1 over s, and then there's maybe divided by a constant and shifted by a constant. So what we're going to have, natural log of 20 minus s over 15. Guess and check is one of the methods for integrals and antiderivatives. Guess and check is always a very good method, and it's probably like the only topic of math where I would encourage guess and check is finding antiderivatives. So an initial guess is I should have something like this: natural log of 20 minus s over 15 as an antiderivative, and then check what happens if I take a derivative of this. I will have 1 over that. Then I'll have to multiply by 1 over negative 1 over 15. So sort of seeing that chain rule, what we're going to want is a negative 15. Multiplying and dividing by constants is kind of an easy thing to just fill in with derivatives and antiderivatives. So now when I take a derivative, I'll have 1 over that, and then when I times this negative 1 over 15, it'll cancel with that, and I'll be back to where we started. On the right, we've just got t plus a constant. And now we want to solve for s. So we've got natural log 20 minus s over 15 is equal to negative 1/15 t plus a constant. So again, we'll be doing this a lot with these constants, as I've been mentioning. I have an arbitrary constant here. I need to divide each of those numbers all over negative 15. But a constant divided by negative 15 is still just a constant. Different constant, but still an arbitrary letter we can use. We exponentiate both sides. So we will have e to the negative 1/15 t plus a c. And again, how do we manipulate this? It's e to the c, e to the negative 1/15 t, which this e to the c is again just a constant. And so we kind of abuse this same letter. This constant, remember, since e to the c is positive, we kind of understand that this constant now, here our c is specifically greater than 0 at this step. And we've got 20 minus s over 15. And then to solve for this, so I can add my s and subtract the other guy over, I'm going to keep my s over 15 is equal to 20 minus c e to the minus 1/15 times t. and then we just multiply by 15. And again, multiplying that constant by 15 again, still a constant, still a positive constant. And this is our equation now that models S. One thing I know was that my initial concentration of salt was 750 grams. Let's see. Because we had 150 liters. Does that number? Those numbers aren't going to work out there because then I'll have 300 minus C. And we would need that C to be negative. What did we miss? Ah, we did miss something. What did we miss? Can anyone see the mistake? So what's our problem here that we're running into? Easy thing to do. If I want to check, I want to solve for C. I want to be able to find this constant. And I should be able to plug in 0 for T and then get 750 out for S. But if C is a positive number, it's going to be less than 300. So something went wrong. We're missing probably a minus sign somewhere, right? It actually seems like this C should be negative. So maybe my assumption with this C being positive wasn't quite right, and it's not. So remember our common things we can miss, absolute value signs in our natural logs. So if we have absolute value signs here, now when I remove the absolute value signs, that gives me a plus or minus there, which means C can be any real number. We saw like one example yesterday. So sometimes you don't need the absolute values if you know what the solution should be. In this case, I think it's because we had our model, we had this minus S that we do want to keep track of where these minus signs are coming in and out of. Okay, so now that we've allowed our C to be positive or negative, we can actually solve for that C. And we'll probably end up finding that it is negative. So how do we solve for that? Our S of 0, we plug in 0 for T. E to the 0 gives me a 1. And I should have initially 750 grams of salt. And then what happens is, so my C is going to be 300 minus 750, which is negative 450. And then our S of T is just 300. Now a negative 450 with that minus sign will make it plus 450. E to the minus 1 over 15T. And this should be a good equation for our system. And we can check. Of course, if I plug in 0, we will get 300 plus 450. We'll get that 750 initially. What is the limit as t goes to infinity? So if we were to let this thing run indefinitely, well, I have e to the minus infinity, which is 1 over e to the infinity, or 1 over infinity. So this term essentially is going to 0, and here we see this limiting constant come out. Is that correct? Is that what we should expect? So that we're saying that if I constantly just let this thing run, ultimately I should end up with 300 grams of salt total in the mixture. which should make sense because we have our volume is fixed, right? And the concentration coming in was 2 grams per liter, which implies that if I only have this concentration coming in now taking over the entire substance, the entire volume of my container, how much salt should I have? The 2 grams per liter times 150. In other words, we should end up with 300 grams. Any questions on that guy? Okay, so let's try to get through a few more examples. These ones might be a little calculator intensive, or at least for some basic computations. I imagine you'll have to do that on WebAssign too. I don't think looking at the problems in the book, which are usually similar to the problems on WebAssign, likely you'll have to use some calculators to round all your decimals and stuff for rates of growth of population and whatnot. Let's take a look at, definitely want to talk about half-life because there's a lot of different equations you can use. You just want to make sure you're consistent. And this is one of those things where on multiple choice, it's a question about half-life. And so depending on how you end up with your answer, you could have the correct answer, but it looks differently, right? We've seen this kind of come up a few times, especially with series, where maybe if you're indexing differently, you get the right answer, but the answers on the multiple choice, they look different. So you got to understand how to manipulate the algebra to make sure your answers are looking like a potential answer on the multiple choice. So let's actually start off with radioactive decay. Sorry, radioactive is actually one word. I put a space there accidentally. Radioactive decay. And we have a problem that says strontium-19, or excuse me, strontium-90 has a half-life of 28 days. And we initially start with 50 milligrams. So half-life, the letter we commonly use is a lambda, just like that. I don't know if you guys have played the video game or seen that symbol wrapped around a circle. So we often use lambda as 28 days, and our C0 is 50 milligrams. So what we want to do is find a function to model it. We want to find the mass after 40 days. And we also want to know how long until 2 milligrams remain. So these are basically everything we can ask for it. Finding a function, of course, will give us this next two. This one, I'm finding mass given the time. And we could always ask the opposite. I could give you a mass and say, how long will it take till I reach that mass? Find the time. So exponential growth is always modeled by a differential equation that is, let's write it as d. We can either write it as dA dt, dp dt. We often use p for population growth. I'm going to use a for amount. I think a is often used in finance as well for accrual. This is common in compound interest. So the amount of our substance, the rate of change we expect to be proportional to the amount left. So these exponential processes, these radioactive decay, the more substance that's left, what does a half-life mean? A half-life means half of the substance remains. So you could kind of come up with a table. We know specific values that at time t equals 0, I have 50 milligrams. At 28 days, I'll have half of that. It will have 25 milligrams. At another 28 days, we will have half of that. And we keep going. Another 28 days. Let's see, what are we at? 84. Half of that, we'll have 6.25. And hopefully you've seen that, well, it's a lot like a sequence, right? What happens if I have a sequence where the consecutive values, if I am multiplying by a constant value every single time, we get an exponential function. So we'll expect an exponential function out of this. K is usually called our growth rate or our constant of proportionality. I think the other term that the book uses, sometimes the book will write the differential equation like this. And if you look at it this way, this is the rate of growth relative to the current population. So another term we call this is the relative growth rate. It's not the absolute growth rate, it is the growth rate as a proportion of the total population. In this case, it is the, I guess, decay rate, since it'll be negative. So we need to be able to use this information of, well, where does this 28 days come into play? And it really just comes in from solving this equation. So now that we've kind of separated the variables, let's go ahead and move our t over as well. This is our equation. Much easier than the last one. When we integrate, we'll get natural log of a is equal to kt plus a constant. And of course, we will get a is equal to some c times e to the kt. And again, I just kind of did some fancy algebra with our c when we manipulate it, just like we did in the last problem. So this is our model, but we've got some dummy variables in there that we want to actually solve for. One thing we can check is that I know that at times t equals 0, I should just have a fixed amount of 50 grams. So in this case, nicely enough, the constant, as we write it, is the initial amount. And we need to find our k. And so we want to use this information of a half-life to solve it. One thing you can always do if you're given data points, if they say something like, on day 28, I have 25 milligrams of the substance. Day 56, I have 12. You can always plot the data points or list them in a table if you want. And then that can give us a way to solve for our constants. In that case, sometimes they don't give you the initial amount. Sometimes they only give you like middle values after so many days. And then you have to come up with a system of equations to solve for both C and K. Hopefully you guys have seen that somewhere, either in pre-calc or calc 1. In this example, I don't want to go through too much of that. Of course, we will have to use at least one data point to solve for K. We already technically used one of our data points to find C. So 0, 50 was easy enough to solve the initial information. How do we find K? You can either come up with a new data point, or you can just kind of intuit what the half-life means. The half-life tells us that in 28 days, I should have half of what we started with. So you can either write it as our data point, I have 25 milligrams left after 28 days, or after you kind of multiply or divide the 50 over, we get that half of the substance is remaining after 28 days. So how do we solve for K? Natural log of both sides. So we've got natural log of 1/2 is equal to 28K. And so our K is equal to natural log of 1/2 divided by 28. You will commonly see this. So natural log of 1/2 is natural log of 2 to the minus 1. So you will often see it as negative natural log of 2 over 28. Either one. I mean, I guess if you leave it in that one or that one, both fine. Sometimes it's easier to write just the natural log of 2 without having that fraction in there. And actually, we may want the 1/2 in here. So one thing I like to do for half-life problems is manipulate how it looks. So you solve your problem, and you get 50 e to the k now is negative natural log of 2 over 28 times t. Good model. That answers question A. But maybe it doesn't look like this. This isn't actually the best model, in my opinion, at least for half-life, because it's a little confusing, especially with the e's and the natural logs. And of course, you should know that every time I have an e raised to a natural log, there's some simplification we can do there. Just got to be careful with the 28. So let's actually write it as 50 e to the natural log of 1/2 over 28. Why do I want to do that? Because I want to simplify this e raised to the natural log. And so I need something like I need just the natural log, right? I need e raised to just that natural log. And so we have to kind of manipulate these constants around that. And our last step is to then pull out the 28. So writing it as natural log of 1/2 kind of gets rid of that minus sign. And now I can write it as e to the natural log of 1/2 raised to the t is staying on the outside, and so is this 1 over 28. So this is just common algebraic manipulations. You should see that if I multiply the exponents, we get right back to where we were. The nice thing about this, though, is that now these e to the natural logs, e's in natural logs are exponentials in natural logs are inverse functions of each other. And so I am just left with whatever comes inside the natural log. And we get this formula. Why is this one a little bit better in terms of the information given? When we talk about radioactive decay and we're talking about specific half-life, I want to know how much time it takes until half of the substance remains. So we have this 1/2. That's pretty nice. And then what was our half-life? It was this 28 days. So it's pretty clear where all the numbers and the concepts were coming from, right? I have 50 milligrams to start with. We're talking about half-life, and the half-life is 28 days. So it's a little bit nicer than having these exponentials and these natural logs of 2s or natural logs of 1/2 in there. And you can check. So, right, what's going to happen? Why does this work? When t is 28, I will just get 28 over 28. That'll be 1. And I will get 1/2 to the 1. So I will have half of the 50 milligrams remain. If t is twice 28, so if I go 2 half-life periods, when t was 56, how much do I have remaining? Well, we cut it in half, then we cut it in half again. We have a quarter of it remaining. So, right, if t is 2 times 28, we will have 1/2 squared, which is 1/4, and we will have a fourth of that 50 milligrams remaining. So that's why I kind of like this one a little bit better. So be careful on that as to which format you use and the which format's listed on the quiz. But that's basically it for half-life. Any questions on that? Okay, so we've got about 30 minutes. Let's do one more example like this. Maybe we'll go through a little bit quicker on growth rate. So growth rate is something similar because I want to do growth rate as well as maybe at least get started on one logistic equation, which we might have to finish up tomorrow. So it's exactly the same concepts as we just talked about. It's just a matter of problem solving. And hopefully you guys at Calc 2 level are strong enough with your problem solving skills and have hopefully seen a lot of this stuff before. Once you get past the initial differential equation, it's kind of just straightforward of pre-calc problem solving. So we've got a bacteria culture grows at a constant rate, and we are told that it has 400 bacterium after 2 hours and 25,600 after 6 hours. So things we want to know the relative growth rate, remember that's our K, the initial size, that was our C in the last one, and of course we have the equation, and then maybe some extra things we'll ask based off of that equation. We'll see what we're at with time. So this is one of the ones where we are given data points. You can put them in a table if you want. So we've got T, we've got at 2 hours, I have 400. Let's use P for our dependent variable. After 6 hours, we've got 25,600. Again, our differential equation to model this is that since we have a constant relative growth rate, we are assuming that the relative rate of growth, the rate of growth relative to the population, is constant, is this K. One thing to note, that K is different than, let's take a look, where's our half-life equation we just finished. I apparently just lost the page we were on. Oh, it's at the top. I'm not looking. I thought I started a new page. So one thing to note, that what was our K in this case? Our K was negative natural log of 2 over 28. So this guy was our K. Or you could write it as natural log of 1/2 over 28. So sometimes it's nice to have that constant rate of growth, that K. But in a half-life situation, we kind of came up with a formula that doesn't even have that in there. If you just go straight from a half-life formula, how would I find the constant rate of growth in this situation? Like if I'm just given, hey, here's a half-life formula, I know that the half-life is 28, we started with 50, you can essentially just write that equation down. How would we find that k? Well, take a derivative. You would take a derivative and then divide by the original amount or the original equation, and then you will solve for your k. So that's one way you can reverse engineer the relative growth rate based on an equation if we are initially given the equation. In this case, of course, we're in the same situation. We are given the differential equation. We are given information, and we want to solve for it. So again, what are we going to have? We'll have natural log of p is equal to e to the kt plus a c, which we move down. So we solve it the exact same way. Of course, I multiply the t's over. When we integrate, I'll get a natural log on the left, and then just manipulate the constants on the right. Oh, I guess I skipping like algebra on different steps. Sorry, natural log of p, we will get kt plus c, and then when we solve for it, we will get p is equal to c e to the kt. So skipping some steps there. And now we just got to solve for our constants. So how do we do that? We need to just plug in our initial information. We're going to get a system of equations. I have two unknowns, my c and k, which means we need two data points, which they give us. So I know that p of 2 is 400. In other words, c times e to the 2k equals 400. And I know that p of 6 is 25,600. So c e to the 6k is 25,600. How do we solve that? We've got 1, we've got equation 2, c e to the 6k, 25,600. Fortunately, these are not linear equations. They're exponential. So linear equations, we usually add, subtract, multiply, divide, add and subtract, and multiply by scalars. There's two things you could do. We could always use natural logs. I could solve for c in one equation, plug that into the other one, solve for k. The other thing we can do is actually divide the equations. So if I take this guy, so if I take equation 2 divided by equation 1, so this is sort of a process that appears a lot with exponential equations. So since exponentials are like a multiplicative process, we can divide them instead of linear equations where we add and subtract them. If I take equation 2 divided by equation 1, what do we get? Well, we'll have c e to the 6k divided by c e to the 2k on the left equals 25,600 over 400 on the right. Zeros go away. I'm going to have to use a calculator for that. And nicely enough, when I divide these, the reason we want to divide is that my c's go away. And so now I can solve for my k. So how's this going to reduce? I have e to the 6k divided by e to the 2k is going to be e to the 6 minus 2, gives me 4k, is 256 over 4. And it looks like we can actually do that number. So what is 256? Is 2 to the 8th over 2 squared. And we get e to the 4k is 2 to the 6th, which is 64. And then solve for k. So natural log of both sides. 4k equals 64. Natural log of 64. And then ultimately, so forgive me for running out of space here, we solve for our k is natural log of 64 over 4. On test quizzes, if the numbers end up being not too nice, you would want to leave it like this. right? If you're not supposed to use a calculator, if we don't want to type this in and get a decimal approximation, natural log of 64 over 4 is what it is. And then based off of that, we can solve for the initial value. Let's see, so we've got P of t is C times e to the kt, which is natural log of 64 over 4 times t. You can leave it like that, or again, we could play some games and simplify this e in natural log if we wanted to. How do I solve for the constant there? Well, we just use any of the other data points. So we had the point to 400. Let's go ahead and plug that in. So I know that 400 is equal to c times e to the natural log of 64 over 4, and then t was 2 there. And so we get 400 is c e to the natural log of 64 over 2. And this one, nicely enough, they gave us nice enough numbers that are all powers of 2. We can solve this guy by hand. If you want to solve it by calculator, try not to if you can, but if you need to use a calculator on some of these, I think some of the numbers aren't going to work out nicely. What are the games we need to play with this e's and natural logs? Well, it is e to the natural log of 64, all raised to the 1/2. And of course, if we work backwards, multiply those two, we'll get that 1/2. So this is kind of how we factor in exponentials, factoring out that 1/2, and now we will get c times those two cancel. So we'll get 64 to the 1/2 equals 400 on the left. And then this is just going to be 8c equals 400. And so our c equals 50. And so our model, P of t is equal to 50 e to the natural log of 64 over 4 times t. Or if we wanted to manipulate this, again, e to the natural log of 64 to the t over 4 is going to give me 50 times 64 to the t over 4. And then we can even take the 4th root of 64. Or can we? What is the 4th root of 64? Anyone know off the top of their heads? So 64 was 2 to the 6th. T over 4, so that's going to be 50 times 2 to the 3/2 t, or 50, 2 to the 3t over 2. Either of these, any of these models look pretty good. This is kind of the most simplified form, I guess, and in some sense gives us the notion of the doubling time. This one gives us the relative growth rate, the constant of proportionality in the exponent. Any questions on that? Okay, so we've got about 20 minutes. I guess the other things that might be asked about this problem is once you have a model of your equation, I could ask questions like, when will 2 milligrams, or this was rate of growth, right? Bacteria. Yeah, so I could say, find the number of cells after 5 hours. How do we do that? Well, I'm given 5 hours, plug in my 5, compute that number. That's how many cells we'll have after 5 hours. I could say, when will it reach 50,000? So now I have a 50,000 for the population. Got to solve for the time, for how long that takes. All that stuff is pretty basic pre-calc skills that I think most of you guys should be pretty comfortable with. And hopefully none of this, most of this was all pre-calc, other than the model coming up with the differential equation is about the only new thing. But even solving that differential equation, as we saw, pretty easy. Let's move on to something a little bit trickier, the logistic equation. We saw the solution for this, or a solution, but we didn't model it as a logistic equation. We were kind of just given numbers. We were given essentially a differential equation and asked to solve it. So we have two situations. Which ones do you guys want to do? We could either jump into some of this COVID data if you guys want to do some real world estimates and use some real world estimates to figure out, well, what's going on in the US, and if the US completely let this thing run uninhibited, how long would it take to essentially develop herd immunity is one problem we could try to figure out. Or we could just do a different example and say that, like, there's brown rats, they grow by a factor of 10 in 15 weeks. And if we have 2 rats on an island that can only hold 100,000, how long till we basically reach our carrying capacity? We could find a model for that kind of situation as well. Any votes? What do you guys want to do?
COVID data.
COVID, good, okay. I didn't want to like scare people with it, but I think it is important, right? This is a math class, and actually I think the biggest problem we have with COVID, as everyone probably understands, is our lack of testing, lack of scientific data, and we really need to educate more people on how to understand exponential growth processes. So let me switch to some of these graphs real quick. So let's come up with some data. So you can see my window. Good things to look at for COVID of what's going on. Johns Hopkins, by far, I think, is the #1 place. They've got really good data. Sometimes it's hard to pick out specifics from here and see what's going on, but they've got a good breakdown of what's going on per state. The other thing you can do is this guy. So if you spell COVID-19 backwards, there's this flip the script, which I think is this whole flip thing, which is why they spell it backwards. If you go to this guy's website, he's a mathematician, and he's got a lot of good data. So if you kind of just click on the first thing, interactive visualizations, you will pull up a lot of graphs that are really useful. So new confirmed cases, this is kind of our sad realization, right? We had it. We had it with the lockdown. All we had to do was wait, but then we wanted to open things up, and we see where we're at. And of course, we could even compare US. I think further down, they have normalized by population, and we kind of see where we're at. Okay, so let's come up with some data. What do we want? We want the growth factor. So when this thing first starts off, we see these exponential growths. So over here on the left, we see this growing exponentially before measures are taken. As soon as we take measures, we see it drop off, and we no longer have exponential growth. Then we relax the measures again here in like June, and then all of a sudden it looks like we've got some exponential growth going on again. And of course, what's going on lately is, well, they're like, hey, we can't sustain this. Let's shut things down again. And so we see it actually starting to curve off. So let's try to model this. Let's go to actually Johns Hopkins. So this is only the new confirmed cases. Let's go to the total number of cases. And total number of cases I found Johns Hopkins, if you go, so I clicked on the US map to give us a map of the US. And then down here in the right, here's what we got. And this graph is the total cases. So you can kind of see where we're at. Let me move the zoom thing. Up here, we are at about 3.9 million cases total that the US has had. This one's a little harder to see, though, so we can't kind of see where the exponential growth starts and ends. Like, we can kind of see the waves of when the measures were taking place and when they were, ended. Let's go back to this graph real quick, just kind of to get our data. So let's use, just because this is an easier graph to see of when the exponential growth is starting and ending. And let's use those dates, and then we will use the total number of cases that we want to model. So let's pick this lowest peak here. I think this is day 97, and it says 18,000 new cases on Tuesday, 2020, 6/9. So let's use 6/9 as our starting date. And let's use, we can use essentially today, even though it is kind of tapering off. We can use today as our ending date. So let's go back to our total cases now, and let's find those dates. So we've got about, so here's 6/5, and then we'll go up to 6/9 here, and we see where we're at. So 6/9, we are at about, what was it, 2 million? So let's write down our data points. So 2/9, we are at, or 6/9, we are at 2 million. And then today, where are we at? We are at 3.9 million. And actually, that's probably not the best number, because where are we at today? If you look over there on the left, whoops, didn't mean to zoom in there. So now it has it broken down by county. Let's go back to the world map. And we're at 3.998 million. So let's go ahead and round that up to about 4 million cases total in the US. So we've got, what's today? July 23rd. So 7/3/23 is 4 million cases. Those will give us some at least easy numbers to work with in terms of the 2 million and 4 million. We will have to figure out the dates. I think actually the dates might be easy enough to figure out, to count it for us, just because our calendar is, monthly based. What date did we pick? We picked 6/9. Is that date? Yeah. So 6/9 was day 97 versus today is day 141. And I think that should be good enough. So let me go ahead and stop the share. Let's work some of this stuff out. So I actually want to count today as day 0, but we want to figure out the rate of growth based off of this. So this is still kind of like in the initial phases of the rate of growth. So we assume it's going to be approximately exponential. So let's approximate this exponential growth using the techniques we were just doing. So we want to find K. And so how many days were between there? What's 141 minus 97? That is what, 3 and 41, so 44. So we can count our points as 0, 2, and then 44 days later, we're at 4 million. So if we want to find this rate of growth, we are going to have the same function. I don't want to go through the differential equation again, because we want to we'll set up a different differential equation once we actually want to incorporate this logistic model that, well, it can't run indefinitely. It's not going to grow like this indefinitely because there's only a finite number of people. So let's just use this to solve for our K. So our C, of course, is 2. And now we can have our K, P of 44 days. is 4, which is 2e to the k times 44. So we get a doubling time. We'll get a natural log of 2 is 44k. And so our k is natural log of 2 over 44. Let me get a calculator. Type that in. And so that's going to be about 0.0157 is our growth rate. And I want to keep this growth rate. We can, do some of those natural log tricks and manipulate this, which actually might be kind of nice just to concurrently with half-life. Sometimes you model population growth by doubling time. You want to know how long it takes to double. And you can, in some sense, reduce it to a base 2 exponential. But let's keep our k because we want to incorporate our logistic model. Namely that the population of US is 330 million. So remember, these numbers, our population here was measured in millions. We were at, 2 million to 4 million number of infected, and it's going to cap out at 330 eventually. If no measures are taking place, of course, it'll get there quicker. If measures are taken into place, well, unless we really shut it down, eventually herd immunity will either take over or there'll be so few cases, and we've learned to treat those cases that we can keep it contained. So what's going to happen if we let it just run amok? Well, we're capped at 330 million people. So what is our differential equation that models this? We mentioned this when we first introduced differential equations. I want to measure, well, what's the rate of spread? So this P is our infected population. And so how should the infected population change? Well, it should be exponential at first. Whenever P is really low, really small relative to the total, right? And we're still pretty much in those days, right? There's only 4 million infected. So we have 4 out of 33, 4 out of 330, not even, just a little over 1% looks like are infected. So it's still going to grow exponentially. But eventually, as the proportion of infected get really close to the maximum value, it should level off. And so we have this product of this factor in here. And why is this? So we've got a 1 because you want to think of this as a percentage. Or how close are we to 100%? When P is close to M, in other words, the proportion is close to 100%, we will have 1 minus 1, which will be 0. Shouldn't have any more growing. We've reached capacity. But if P is a lot smaller than M, then our P over M, the proportion of infected, is really small. It's close to 0. Or maybe it's even, 0, even 1% is only that. And so what's going to happen, we can approximate this differential equation because that's going to remain constant at least for a short period of time. And the differential equation should be close to something like that, which is, really the same equation as an exponential model that we've been solving. So now with this extra factor in here, it models our our capacity, our carrying capacity. And so what we want to do is now solve this. We know our K is our 0.0157, and our carrying capacity is 330 million. Let's go ahead and solve this. And let's solve it as it is, just to keep the constants as they are without having to plug in, decimals and everything. And we can plug in those constants at the end. So we've only got a couple of minutes. Let's go through the first steps fairly quickly. We've seen how to solve these guys. It is just a separable differential equation. And I'm going to do some algebra fairly quickly. 1 minus p over m equals dt. And of course, we want to simplify this guy. One thing we can do is multiply by m over m. So if I multiply an m by the bottom, I can distribute it. And it'll look like that. So I have m over m in the numerator, and of course, producting, I can move the m and then distribute it through that guy. We'll get those there. It just makes it a little easier instead of dealing with that fraction, and we want to separate it. So we have now a over kp plus b over m minus p is equal to m over that guy. Got to go through our separable equations, solve for our a and b. Once I do that, then I can integrate both of those terms, and we've got to solve those again. So we can go through that really quickly tomorrow, and then go ahead and move on with, what are we talking about tomorrow? I think we have one more topic on there, or are we finishing up with, let me check the schedule real quick. See how much time. I think we should have enough time to finish this. Yeah, so we only have a project tomorrow, Torricelli's law and separable differential equations. So we can go ahead and kind of warm up with this tomorrow, finish our model of our logarithmic or our logistic equation for this COVID-19 growth, and then we could jump right into more separable equation practice with the project. And then office hours in the evening, and hopefully you guys will get set up and squared away for the exam on Monday. Any questions?